All right, we have here today another integral from MIT 2022 regular season 19. I did this one in a previous video using integration by parts, and for this one I want to use the complex method on it. We'll just look at Euler's formula really quick. So that's going to be EIX is going to be cosine of x plus I sine of x. Now for our problem, we have the sign here. What we could look at is what happens when we input an ln x for x, just plugging it into this same formula. Now, first of all, just with log properties, e to the ln x is the same thing as x, so this is actually the same thing as x to the I. But then plugging in on the right side here, we're going to have, this is going to become cosine ln x plus I sine ln x, and that's exactly this thing right here over here. So the part we're interested here, this is going to be the imaginary part. So here we could call this thing the imaginary part of xi. But actually we can wrap that around the whole integral, because the x squared doesn't really change anything, because it's just going to be not, I wanted to say like a constant. It's not actually a constant, but it's not actually a constant, it's just that it's strictly real. So we can just kind of bring that as like a constant into the expression and wrap this around the whole thing and say we want the imaginary part of x squared times xi dx. The reason for doing it, well, now we've got the same base and it's just going to become power rho. I'll drop this for now and we'll just bring it back later just so I'm not rewriting it, but it's always going to be there. So adding the exponents together, we can write this as x to the 2 plus I dx. And then again, this is just a constant, so when we integrate, we get x. Adding 1, we get 3 plus I over 3 plus I. So you can see the integral is really simple. All the work is actually just trying to get back to how you're going to represent. I don't think MIT would accept it in this form, even though it's kind of a solution, right? But we want to get it back and write it something like this. And we also want to see the solution we got in the other video. So we can break this up again and write it as an x cubed. And then we'll have left an x to the I. But we can just go backwards over here and write it like that. But really what I want is we want to get trig functions again. So instead, let's go this way. And we'll call this cosine ln x plus I sine ln x. And then all we need to do really is, let's use the conjugate to rationalize this. So I can multiply in 3 minus I over 3 minus I here. When you distribute out the denominator, this is just going to be a 10 right here. You can just multiply that out. So then let's kind of FOIL out this part, but we'll take the 10 and divide it into the x cubed. So what we have is x cubed over 10. Multiply all this stuff out, we get 3 cosine ln x plus, I should probably order it more carefully, but I'm just feeling, let's just do it and see what happens. So then we'll have minus I cosine ln x. Here, minus I times I is going to be a positive 1. So we're going to have positive sine ln x. But I think this is a good point to bring back this thing, because in the end, what we want is the imaginary part of all this stuff. So that's going to allow me to disregard any of the real parts. So like, in reality, we should maybe write it out cleanly, but I think you can see that the imaginary part is going to be with this stuff and this stuff. This is going to be real, this is going to be real. And when we take the imaginary part, we actually just drop the I, drop it there. And so we can put this all together. For the final solution on it, we just get x cubed over 10 times 3 sine ln x minus cosine ln x, add a plus c, and that's it. All right, so there you go, pretty easy. Probably easier than the integration by parts in a lot of ways, although I guess there's more work in the end just cleaning it up. So if you count that, then who knows. But anyway, there you go. That's it for today. Thanks so much for watching. Have a good day.